Hi, this is a respiratory physiology video. Dr. Hudson, and what I'm going to try to do in this video is simplify the idea of how gas exchange can occur. And I personally feel that there's one equation that you guys can all learn. Now, you can learn it in the physics format, which is extremely complicated, or you can learn it in my physiology format, and I try to simplify the heck out of it, so I recommend learning it that way. But there's one equation called Fick's law that describes gas exchange very, very well, because Fick's law relates to the rate or the speed that diffusion can occur. So Fick's law is all about the rate of diffusion, the ROD, the rate of diffusion. And the rate of diffusion is proportional to some things. That means, remember, proportional, little fishy sign, that means what happens on the right side of the equation affects what's happening on the left side of the equation. In other words, whatever happens on the numerator on the right hand side is going to be directly proportional to the left side. If this numerator increases, then the rate of diffusion will increase. That's what directly proportional means. And if it's on the bottom of the equation, if it's part of the denominator, then it's the opposite. It's inversely related. So if the bottom increases, since it's inversely related, then the top will be the opposite, right? The rate of diffusion will be the opposite. The last little bit of introduction that I'm going to always try to do when I'm introducing equations is I'm going to make sure that you guys are aware that the right side of the equation affects the left side, but the left side does not affect the right side. So just because we change the rate of diffusion doesn't mean we know which variable gets changed on the right side of the equation. So keep that in mind moving forward. Diffusion. We need to try to remember what the word diffusion even means. Okay, so when we're dealing with diffusion, remember what we're dealing with is passive energy. Diffusion is passive energy. It's things that are diffusing from an area of high concentration to an area of low concentration. So we're dealing with passive energy. And things are moving from an area of high concentration, the brackets mean concentration, to low concentration. So high concentration to low concentration. That's what passive means. The rate of diffusion, the speed that our things are moving from high to low. So, what's going to be the first thing that affects whether or not diffusion even occurs? Well, the first thing we must have is a high to low. Right? This is related to a gradient. Okay, this is a gradient. The gradient of anything is equal to the difference between the two sides. Difference. I can spell, I swear. Okay, difference between the two sides. So for instance, a concentration gradient, if we come over here and say this is a cell membrane, well, what if the concentration on one side of this membrane up here was, I don't know, let's use sodium as our example, because why not? Doesn't really matter. Right? And we said that there are 5 sodium up here, and there's 1 sodium down here. So what's the concentration gradient? Subjective. We just introduced some stuff, so it doesn't really matter. The difference between the two sides means you just take the two sides and subtract them, right? So 5 minus 1, the concentration gradient here would be 4. What would happen to that concentration gradient if we added some more sodium on this side? Well, now it's 7 minus 1, so the concentration gradient just became 6. So we went from 4 to 6. So what happened to the concentration gradient? Increase, decrease, no change. The gradient just got bigger. So now what we can think about this like is a hill, right? When the concentration gradient isn't very steep, things aren't going to move very fast down that hill. But as we increase the concentration gradient, as we make the hill steeper and steeper and steeper, things can move faster and faster and faster. So the first variable that is going to impact the rate of diffusion is going to be the concentration gradient, or just the gradient. because we're not always dealing with the concentration. Sometimes we're dealing with partial pressures and all that other stuff. So the first portion of the equation we need to think about is the gradient of whatever we're looking at. The second part of the equation that's important, let's actually just refer back to our equation and say what we just said. So what happens if the gradient increases? What would happen to the speed at which it traveled? It would increase as well, right? What happened if the gradient were to decrease? Well, then the speed at which it travels, the rate that it can diffuse, decreases with it. So let's erase our little funny hills, our little lines. Let's erase our sodium here, because we're not ultimately after sodium. We're dealing with the respiratory system. And we want to see how things can move through the cell membrane, because obviously sodium can't do that. It's going to need help. So we're going to refer back to that in this equation as well. The second part of this equation that matters is going to be the surface area. So we're going to multiply gradient by the surface area. Don't worry so much about the multiplication. It's just dividing these two variables. So the second thing has to do with the surface area. So SA, capital SA equals surface area. And the way to think about the surface area is the more area there is for things to diffuse across, the more diffusion can occur, and the faster it can occur, right? So, in other words, if we were to have something that looked like this, if we had a surface that looked like this, it has a very large surface area compared to a flat surface. Okay, this surface, the area that comes into contact with the surface would be every little bit of this. So if we were to measure the entire length of that curve, it would be much, much longer than the length of that curve. So as the surface area increases, what happens to the speed that diffusion can occur is going to increase as well, because it's directly proportional. It's a numerator. It's on the top of the equation on the right-hand side. The last part, the last variable that's going to be directly proportional with the rate of diffusion we want to learn about has to do with the permeability of the membrane. We're going to go MP, capital M, capital P, where this is related to the membrane permeability. Okay, membrane permeability. Membrane permeability goes back to a little bit of chemistry, and it relates to whether the membrane, well, whether something can go through it or not. And remember, the membrane, this is a phospholipid bilayer. You might have to go back and review this material, but what that means is that you have polar ends that are hydrophilic. They're reaching out to the fluids because they're hydrophilic. They love water. And you have non-polar ends that are trying to get away from water all the time. They're hydrophobic. So things that can go through the membrane freely are going to be other non-polar objects. So polarity of the molecule alters the membrane permeability. The more polar something is, the less likely it can go through the membrane. In addition, the molecular size has a huge impact. The bigger that molecule, well, our big thing's going to be able to go through a membrane easier or harder. The bigger it is, the slower it moves. So the membrane permeability is related to a couple things. It's related to the chemistry of that covalent bond or the ion or whatever it might be. Can it penetrate the membrane? Okay, so I'm typically going to say charged or not charged. And what we're talking about here is the molecule that's trying to get through. In other words, polar versus nonpolar, but it's not always polar. It could be something like sodium, which is an ion, which has this nice big charge hanging off of it, and it can't get through the membrane very easily. The other thing that's going to impact it is the size of the molecule. But this one, as the size gets bigger, the membrane permeability gets smaller. So hopefully you guys can see that we actually have an equation that we can use here if you want to. Membrane permeability is proportional to that chemistry, so the permeability of the molecule, and as that permeability goes up, well, then it's going to go through the membrane easier. So nonpolar molecules are going to be much more permeable. Nonpolar can go through the cell membrane. Again, you may need to review this if you don't remember your chemistry. And this is all going to be divided by the size of the molecule. Because as it increases in size, the permeability goes down. So these are inversely proportional to one another. So as the membrane permeability goes down, let's just use that one, what would happen to the rate of diffusion? Well, that means it's not passing through the membrane quite as well. So the speed that it can pass through is going to decrease as well. The last thing that we want to think about is actually the most important variable. True, you must have a gradient or none of this works. So really you can argue that that's the most important variable. Because if gradient is 0, then everything's 0. However, we're going to be looking at the distance that this molecule has to travel, and we're going to say it is more powerful than everything else. So mathematically, we give it a squared factor. So every power that goes up, right, that changes the fold impact that this particular variable has on the equation. We give it a 2 power, it's stronger than anything else. If we change the distance by 2, well, that's 2 to the 2, so we're actually changing it 4-fold. So this is the most impactful, the most powerful determinant that speed of some diffusion relies upon. And since it's inversely proportional, as the distance increases, what would happen to the speed things can travel across it? It decreases. So let's look at all of these variables with our membrane, our little just sketch, right? This is the polar size. There's our peanut butter core. It's our phospholipid core. So this is the phospholipid bilayer. And we're going to use, since we're dealing with the respiratory system, we're going to say that what we're dealing with is oxygen. We should also think about CO2, but let's start with oxygen. Okay, we're going to actually say that we have the alveoli here. And there's actually 2 cell membranes and a basement membrane that oxygen has to travel through to get into the blood. We're going to say plasma's down here, but we're going to simplify it. Guys, don't think this is the real deal. This is just simplification because we want to understand the subject and we don't want to get bogged down in the details. So we're going to say this is the alveoli and this is the plasma. And if oxygen wants to get into the plasma, what variables affect how oxygen is being transported? Well, the first variable must be the concentration gradient. It's actually the partial pressure gradient. So the partial pressure of oxygen in the alveoli, if I want to get oxygen to move down into the plasma, then the partial pressure of oxygen must be higher here than here. In order to move oxygen into the plasma, the partial pressure of oxygen in the alveoli is much, much higher than in the blood. And in fact, the returning pulmonary arteries, right, bringing poorly oxygenated blood back to the lungs so it can become oxygenated, that blood is only about a partial pressure of oxygen of approximately 40 millimeters of mercury. And the partial pressure of oxygen inside of our alveoli is approximately 104 millimeters of mercury. So what does that tell you? Oxygen's always trying to move down its gradient, move down the hill passively. And can oxygen just pass through the cell membrane? Heck yeah, it can. Because oxygen is about as nonpolar as it gets. Oxygen bound with an oxygen, O2. Covalent bond, equally sharing those electrons. This is about as nonpolar as it gets. And it's tiny, it's just 2 oxygens. So is the membrane permeability of oxygen high or low? it's extremely high, right? So the membrane permeability of oxygen is really high, therefore the diffusion of oxygen occurs very fast. That just has to do with the membrane permeability. And there's also a large concentration gradient that's available. Right? We already have a gradient, therefore we already have a speed that that diffusion can move. Now, what would happen if we increase the amount of oxygen that we're breathing? What would happen if we increase the partial pressure of oxygen in the air that we're breathing? Let's pump it up. Okay, let's jump it up. Let's jump it up to 200, because why the hell not? Right? Let's say we got 200 millimeters of mercury. What just happened to the gradient? We went from 104 minus 40. We went from 64 to 200 minus 40. That's 160. So we went from 64 to 160. The gradient just skyrocketed, right? And as that gradient increases, the speed that the diffusion can occur goes up. You've got to think about this medically, right? We give patients that are having breathing issues, we give them oxygen tanks. Why do we give them oxygen tanks? Because that increases their partial pressure gradient of oxygen, their concentration of oxygen. The gradient gets bigger, therefore the speed at which the oxygen gets into the blood starts going up. Surface area. Your lungs have a very large surface area. Each one of those alveolus is tiny by itself. But when we start adding together all the millions of alveoli, and if we took and spread them all out, they would actually take up the area, the surface area of about 2 tennis courts. They're huge. So they have a very large surface area to begin with. But what happens in a disease like emphysema, where the lungs get eaten away, or fibrotic lung disease, where those alveoli can no longer expand to the degree they once did? The area, the interactive surface area that air can diffuse across in all these different scenarios starts to decrease. And so if we have a disease now that decreases that surface area, well, what's going to happen to the speed of diffusion across that? It's going to decrease as well. But what do we give those patients to try to fix their oxygen issues? We give them pure oxygen. And that is going to try to balance the total amount of oxygen in that patient. As their surface area drops, we give them oxygen to try to balance out that rate of diffusion, bring you back to homeostasis. The last variable to think about is distance. And the distance between the alveolus and the plasma is small. Again, it's 2 layers of simple squamous epithelial tissue, one from the alveolus, one from the endothelium layer that's lining the blood vessels, lining the capillaries. And there's a very small fused basement membrane between them. That's a very, very thin layer that oxygen is trying to diffuse across. So the distance in your lungs is naturally really, really small. The distance in your lungs is naturally small, so really short distance, really fast diffusion. But what starts to happen in a patient that has, for instance, pneumonia? Okay, what would happen if you started to build up water here? That's what pneumonia is. It's water that's building up inside of the alveoli. It's coating the surface. Well, now we got a non-polar molecule trying to go through an extremely polar molecule. This is a hydrophobic water molecule. This is a hydrophobic oxygen molecule trying to go through water. It's going to have a hard time doing that in the first place. So the membrane permeability starts to drop. In addition, water is a distance. It's a barrier. So it starts adding distance that oxygen has to travel. So not only does the membrane permeability goes down, the effective surface area for diffusion goes down, and the distance these things have to travel, let me use my colors properly here, and the effective distance that this stuff has to travel is going up. That's pneumonia. And that's how we can use Fick's law to understand diseases. That's pneumonia. the membrane permeability starts to drop. The surface area, the effective surface area for diffusion starts to drop. The distance things need to travel starts to go up. Holy crap, let's look at what happens over here. The effective membrane permeability just drops, so the rate of diffusion drops. The surface area just decreased, so the rate of diffusion drops even more. The distance it has to travel increases, so it decreases the diffusion even more. And this is why pneumonia has killed more people in the world, in the history of the world, than any other disease. Pneumonia is nasty. A lot of other nasty diseases out there, including the one that is making me teach from home right now, COVID, right? COVID causes alveoli to collapse and causes secondary pneumonia. So the surface area is dropping just because the alveoli are collapsing. Membrane permeability is dropping because of the water in the lungs. The distance that things have to travel is going up, but it wouldn't even matter because if the alveoli are collapsed, then air can't even get into the lungs to begin with. All of the diffusion into our blood is decreasing, and these patients feel like they are short of breath, starving for air all the time. That's because their brain is screaming at them that they're not getting enough oxygen, so the level of CO2 in their blood is going up. It's a whole cluster. What do we try to do to patients that are in severe pneumonia, severe emphysema? If we can't fix that disease, they're probably not going to make it. But in the interim, we can try to give them oxygen. We can try to give them medically grade oxygen, 80, 90, 98% pure oxygen, and that's going to try to drive up the diffusion at least a little bit, try to offset the disorder, the patho, whatever it may be. In my opinion, Fick's law pretty much describes every single lung disorder, every single lung disease on the face of the planet. They're going to try to impact, most of them are going to try to impact at least one portion of Fick's law, whether it's the surface area membrane permeability, the gradient that's available, or the distance something has to travel. Keep that in mind as you're studying respiratory physiology, and it will help you out a lot. Alright, this is Dr. Hudson. I'm talking about gas exchange in the respiratory system. See you in my next video. Humankind, be both.